Hi, this is Bert de Vries, and this is the Bayesian Machine Learning and Information Processing class. And today we're going to be talking about regression. Now, regression, as you know, is probably the most popular tool in science. Another word for regression is curve fitting. And the idea is you collect a bunch of data, here indicated in this example by the blue dots, and you want to find the best curve through these data points. And that's, of course, a very typical question in all of science, that way outside engineering. So this question, okay, what is the best curve, is really a difficult question. There isn't really a unique answer to that. If I would limit my model set to, let's say, second order polynomials, then I would never get the green curve that is shown here. This seems to be like a sinusoidal signal, and with a polynomial, second order polynomial, I'm not going to be able to draw that curve. So I would get a very different curve. So the best curve is really not just a function of your data points, but also of your model assumptions. Now, the nice thing about the Bayesian approach is that you have to be very explicit about your model assumptions. I'm sure you've done curve fitting before in some of your classes. The usual approach is to do, let's assume some polynomial, and let's minimize the sum of squared errors. And there's nothing wrong with that. And in fact, in this class, towards the end of the class, we will compare the Bayesian method against that method. That's not something that comparison, I'm not going to do that in this video. I want to keep the video short as usual. So I'm just going to concentrate on what Bayesian linear regression is, just the essentials. So we observe a bunch of data points, x1, y1, x is the input, y1 is the response. And note that they both need to be given, both need to be observed. We're talking about supervised learning here. One way of going forward is to just say, oh, x1 and y1, that's a vector, I'm going to call that new vector x. And so I have x2 and y2, I call that, that's my second vector, x2, and so forth. And then I'm just going to do density estimation. And right, so the probability for pairs xy, and then from that joint distribution, I can basically obtain anything that I want, and that's totally true. What we usually do, though, is we assume that the inputs x are given, that there's no noise in the measurement of the input. I give you an x, and I just want to know, give your prediction for y. So really, we're interested now in a conditional distribution. The probability distribution for the response is y for given x. As I said, that's not the only way how you can phrase this regression question, because there may also be some measurement error in x, but this is by far the most common approach. So we're interested in creating or in finding, parameterizing and finding the parameters for a model P of y given x. As usual in this class, we will proceed by first making a model specification. We'll do inference, and we'll do a prediction application. The underlying model for regression is nearly always stated in this way. Y of n, the response, is some function of x. That function has parameters, and so this function tries to predict y of n, and there may be an error, and these errors are caught by a noise term. Now, in linear regression, that means it's going to be linear with respect to the parameters. We're going to assume that this function is basically a linear function of the parameters. So we allow to take nonlinear features of the inputs. Phi of j could be any kind of function of x of n, and but with respect to w, this is a linear function, right? For any x of n, we can always just execute this function phi1 and phi2 and until phi m, and now I have m numbers, an m-dimensional vector, right? And but just for simplicity, because I don't want to keep writing this guy all the time, I'm just going to assume now that we do really linear regression and also linear in x. So x of n is its own feature set, and x of n is going to be m-dimensional. Okay, so now we have linear regression. Now, if we also assume that this noise term here is Gaussian, then we talk about ordinary linear regression. So we've really made it simple now. Y of n is just a linear function in W. For simplicity, we also keep it linear in x, but we don't use that. You may also see read any kind of feature of x here, plus Gaussian noise. Okay, so that's our model. We have a data set, so let's proceed. Let's do inference. Let's first rewrite this though, before we do inference, in a likelihood. Then I need to collect basically all my data points, right? And it is a useful way to do that is to just collect all these data points, all these observations in vectors. So we're gonna now write this. Y is y1 through yn, and is the number of observations. We're gonna collect all the inputs in a matrix X here. So this is basically horizontally X1, and here is X2, and here is Xn horizontally, and this is my W. This is all given. These are all data points. This is all given. These are all numbers as well. This is really the variable that we're talking about, that we want to estimate. And we're going to put that all together in a Gaussian over Y capital X times W with a variance beta minus 1. This is now our likelihood. Now, if we want to do Bayesian inference for W, we're going to have to choose a prior for W. You won't be surprised that it comes out the best, and it's if we choose a Gaussian prior for W. And we've also discussed in the Gaussian class why that's actually a pretty good choice. So let's choose a Gaussian prior for W. So now I have here a likelihood function. This is a likelihood function for W because we assume beta is given and X and Y have been observed. It's our training set. So this is just a function in W now. This is also just a function in W. And we're going to assume alpha and beta are given. Normally they may not be given, and you also have to estimate them. But that's not going to be analytically very pleasant, so we're not going to do it in this class. You're going to have to do that with probabilistic programming languages, some of which what we will discuss later on in this class. So let's do inference, right? We want to come up with, we have a prior for W. Now let's come up with the posterior. The posterior for W, given all the data, is the likelihood times the prior. This was the likelihood times the prior. Oh, you'll say, hey, so this is a Gaussian times a Gaussian, going to get a Gaussian. Yes, you will get a Gaussian, but this is a Gaussian in W, and this is a Gaussian in Y. There is a W, we can exchange these two, but then it's still a Gaussian in X times W rather than just W. So the multiplication formula cannot be applied straightforwardly. What we can do is just work out the exponent of the Gaussian by just writing out basically this, the exponent of this Gaussian, which looks like this, and the exponent of this Gaussian, which looks like this. So let's multiply that all the way out. I'm going to get a second order polynomial in W. half times W transpose something times W, and this is a linear function of W, and this has nothing to do. This is not a function of W. Now, if you would go back to your Gaussian class and you look at the natural parameterization of the Gaussian, you'll see that we can also write the Gaussian in this way with this second order polynomial. And then you'll see that what's in between this W transpose and W, that's exactly the new precision matrix. And this guy here is the natural mean, the precision weighted means. So we can immediately write down now the answer. This posterior is going to be a Gaussian. We're going to parameterize it with canonical or natural parameters. Eta after, meaning eta after n observations, and precision lambda after n observations. And they are given by these formulas, which I take straight from here. And you can also now return to the moment parameterization if you want. That's not necessary, but you can. Let's now see how this works out in some graphs, because and this is quite interesting, I think. I think you should really try to understand these graphs. We do this, we have a very simple model. It's a linear model, so we are working on a line. We want to discover, we have two parameters, omega 0, or W0, and W1. And so we start with no data observations, nothing. So I have to start with a prior. So let's start with a prior centered on 0, a prior for W, WO is here, W1 is here. So this is just some Gaussian centered around 0 with variance beta minus 1. And what we can do now is just draw some random samples from this distribution. So we're going to get values then for W0 and W1, plug them in here and draw the line. And then you get a line like this. And if I draw another sample from this distribution, I don't know, let's say around here, I'm going to get a line like this. And I do this a few times, and then you'll see that if this is my knowledge about W, I still have, it could still be any line, right? Now we draw the first data point. We draw this point here, this blue point. What we'll do is we'll write down, we plug that in our formula for the likelihood, right? This was our likelihood here. And so we plug that in y and x, and what it comes out is basically a function, a Gaussian for W that's very elongated, right? That's really elongated in this way. This white cross here is basically the real value for W, but we don't know that. We have no idea what that is at this point. We just draw this one data point. We can write out a likelihood, which looks like this, a very elongated Gaussian. And we have to multiply it with our prior right here. And if we multiply this guy with this guy, we're going to get this posterior. This is also a Gaussian now, right? Now, if I draw samples again from this whole space, most of the samples are going to be around the around what's red here, right? I'm going to get very few samples from what's dark blue. So these samples omega, or these samples W, are going to be pretty close together. So, and you already see now, if you draw the corresponding lines, that there is a sort of a pattern. There's already some certainty about basically where these lines lie on the right hand side. Here on the left part of the graph, not yet. But we're going to get another point. We're going to get a third point, or a second point right here. I'm going to write down a likelihood again. I'm going to multiply this likelihood with this prior, which is basically the posterior after the first sample, getting a new posterior right here. And now, if I draw points from this posterior distribution, they're going to be mostly located here, very close together. and you see the corresponding lines already are getting very close, getting very basically located in a very tight cylinder in the plot. We can keep going. We can keep going, drawing lots of data points, making likelihoods, and we'll get closer and closer to the real point. But there is a remaining uncertainty, and so there's also some remaining uncertainty what the underlying pattern is, and that's totally correct. There are always the next point could be here, right? It could be here. There is always some remaining uncertainty what the remaining points will be and what the underlying pattern is. Now we can also, having this posterior, write down in this an expression for the predicted distribution given some new data point x and given the data set, but we're going to translate that, of course, to the posterior of the weights. What is going to be the probability distribution of a white bullet, right? So this guy, as before, what we do is we extend the conversation to include our model. This is just, let's say, this doesn't include our model yet. Here it's given the data. Here it's now we include our model. In our model, this was a model assumption, the data generating distribution. And this is what we know about the parameters of the model after having seen the data. We're not interested in W, so we integrate that out. And you can work out that that leads to a new Gaussian distribution for Y. Let's also have a look at that in another example. I have a synthetic sinusoidal data set. So basically this is my data set. I'm going to draw from, add noise and draw from this, basically from this data set, this green curve plus some noise. I'm going to draw data points. I'm going to do linear regression in W, but now I'm going to have some basis functions of x of n. I'm going to use these, I'm going to use 9 of these sort of like Gaussian basis functions. So I have a 9-dimensional regression problem, and again we're going to assume this noise. Now after I've seen one data point, I can update my posterior for my for W, and using that posterior I can actually work out this integral and come up with my distribution for Y. And what you'll see is in this problem that what I know about the curves for Y is indicated here by the shaded area. This is the mean. This is sort of this is the mean prediction of the green curve, and this is the uncertainty. So in this vertical direction it's a Gaussian, and in this vertical direction also a Gaussian. The important thing is around the data point here I have less uncertainty about where the green curve lies than here and here, because I haven't seen any data yet. If I now draw curves out of this, let's say draw samples from my posterior for W and create new curves just like I did here, then the curves corresponding to one data point look like this, right? So they're all over the place, but they kind of come together around here. You can do the same for 2 data points. Again, not much uncertainty around here, but lots of uncertainty yet still where I haven't seen any data. I can make new curves again, and we see that also here, right? So not so much uncertainty here, but lots of uncertainty here. We can keep going here after 25 data points. Now the cylinder is kind of tight, and here are the curves. And again, we can keep going, drawing more data points, and we'll get closer and closer to this green curve. We'll never 100% reach it because it's a finite data set. There is always some remaining uncertainty. Okay, so this is the basic idea of Bayesian linear regression. I think the interesting thing here is to recognize how after each data point, when you make an update, you see your posterior getting closer to basically the real data point of your underlying mechanism, and also the parameter, and also you'll see that the predictive distribution or the predictive distribution of y of your response gets closer and closer to the underlying mechanism. And you also notice that when you draw some data, that you are going to be more accurate around the areas where you draw the data, and you're going to be less accurate where you haven't seen the data yet. And with that, I think I want to end the linear regression lesson. There is more to read, so please read the notebook. And as usual, if you have any questions, just write them down, submit them, and then we'll talk about it in class. Bye-bye.